Good morning, FOR 345. Good to see you again. It's your second day of a virtual lecture, and I'm here to lecture you virtually, so we'll have a little bit of interaction. So today we're going to pick up where we left off, but first I've got to show you my favorite non sequitur. It kind of describes how girls are made. So that's pretty good. I won't show you the one how boys are made because it's a little more graphic and not so. And since I being a boy, it's not so compelling. So with that, it's time to think about where we've been and where we're going. And so here's where we've been. If you remember last time, we wrapped up wind erosion. We talked about the impacting factors. We talked about wind velocity and wind turbulence and so forth. And then we kind of talked about the soil properties, went down through bulk density and crusting and all of those. And we kind of concluded thinking about the good news about erosion. I pointed out a study that looked at the Coon Creek Basin, and an actual monumented study that started in 1938 and continued on into the late 90s that actually measured the impacts of erosion in terms of depths, and that was published in Science. And so that, along with the graph provided in the book, showed us that the positive impacts of erosion control have been felt and have been very, very nicely received. Then we took off and we started talking about aeration. And so we spent some time defining aeration, looking at the factors that contribute to aeration, and we moved on with some kind of way to assess this quantitatively. And I gave you 4 or 5 different ways and 4 or 5 numbers. We had cutoffs for oxygen diffusion rate and macroporosity and air-filled pore space and a variety of numbers. And that gives us a way now to quantify, and so I can actually ask you if I have a well-aerated soil or what your opinion would be based on some of those data. And so that's kind of where we pick up. And we were looking at assessing aeration, and we were kind of talking about EH, this idea of oxidation and reduction. And oxidation being the gain of a valence state, or the loss of electrons, and reduction being the gain of electrons. And then we started talking about iron. So we'll kind of pick up there, pick up those equations to kind of get you thinking in terms of electron transferring, in terms of oxidation reduction, because the next piece ties all of that together in terms of EH and dissolved oxygen. And so we'll continue on with the story, and off and running we go. Okay. So last week, or 2 days ago actually, we looked at this graph, and this looked at a number of different processes, a number of different measurements, and on this axis we had EH, and again we had measured in volts, and we've gone from 0, 0.2, plus 0.4, and then we get down to negative, and we were looking at days after saturation. What happens after you saturate a soil? And we decided that the dissolved oxygen, which is shown here in milligrams per liter from 0 to 8, dissolved oxygen drops off extremely rapidly. Okay, it's less than a day, and that dissolved oxygen is pretty much dissipated and used up, and it's at very low levels, below aerobic levels, and then it finally drops off further. Okay? We also looked at EH. It drops off rapidly from 0.6, and this EH reduction pretty much parallels the reduction in dissolved oxygen. And so we're going from 0.6 volts to 0.2 down to 0 and negative numbers. And then we're hovering at negative numbers. Okay? And we also noted that the pH, which we haven't defined yet, and actually next month we'll give you a really good definition, but the pH, the acidity, tends to be reduced, the pH rises. All these things going on. At the same time, we're way below the reduction of iron. So all this time, iron's being reduced. Okay, above this line will be oxidized. Of course, it's not above that line. As soon as we get down here, past 2 days past soaking and saturation, we're in trouble. Well, if you're an aerobic organism, you're in trouble. And so that's where we pick up. Okay, so we looked at this graph. It showed the EH, and here's in millivolts. And we've already been thinking about volts. And again, it's 10 to the minus 3 milli. So if we go back to our other slot, we're looking at 0, 0.2, 0.4, 0.6 volts. So how many volts is millivolts is 0.6? Okay, we multiply that actually we divide that by 1,000, we get to millivolts. And so 600, sorry about that. Let me pick up where we're going. So here in millivolts, 0.2, we multiply that times 1,000. Okay, we get to 200. And so we just see the same scale. Okay, 1,000-fold difference. So whether we're in volts and millivolts, it should be fairly easy for us to think about this. Okay? And then we had this graph relating this EH potential in millivolts to oxygen diffusion rate. And we've already said that both of these are useful. And the cutoff for oxygen diffusion rate, comparing the top growth and bottom growth ceasing right here about 0.2 to 0.3. Okay? And that compares to an EH right a little bit above 200 millivolts. Okay. Okay, and then we'll revisit this equation again. We'll revisit what's happening with iron oxidation or iron reduction. And we have this simple equation, iron oxide with a valence of +2 and in water. And when there's oxygen around, that iron is oxidized. And here's the oxidation. We're going from +2 to +3. Okay, this is a loss of electrons going to the right. Electrons are lost, iron goes to the +3 state, and electrons are generated. Okay? So this is electrons are generated in the process of many processes. And one way to do that is respiration. So we asked, iron is oxidized, where the electrons went. Okay? Those electrons actually went to oxygen. And of course, in order for electrons to go to oxygen, oxygen has to be present. So oxygen is reduced to water, iron is oxidized. And this happens when there's plenty of oxygen around. Oxygen itself is reduced. It gets the electrons, it's reduced to water. Okay. No problemo. So you put that all together, and the thing that we're used to seeing, we kind of hid this before in our earlier discussions of oxidation reduction. We were talking about modeling and so forth. We hid this piece, and we just added it together. And so what you saw before was FeO +2 in the presence of oxygen going to FeOOH +3. And that's what you see. And now it's more explicitly, we've identified in this graph that oxygen is definitely getting those electrons. Okay? And the valence of iron +2 to +3, oxidation of iron. Okay. So there are other ways to do this. So we were talking about assessing aeration, right? I gave you some oxygen diffusion rates, some numbers for a variety of things, macroporosity. And another way to assess aeration or reduction, oxidation, is visually, something called iris. And these are indicator of reduction in soils tubes. And these are pretty new, relatively new idea. And here are some tubes. So these tubes, these are the top, okay? And this line represents the soil, where they're buried in the soil. And so these tubes are coated with an iron hydrite material, okay? And so if this iron is reduced, it chips. So when iron is reduced, this paint peels off. So this represents iron reduction. Okay? Okay? Here, very little iron reduction. This is site 1, site 2, site 3. Okay? And there's a little less reduction. But anytime you see this peeling off, this is the reduction. It's due to the reduction of iron. This paint, it reduced, and when it's reduced, it peels off. Pretty cool idea. So here's a visual representation showing the reduction of iron is going on. It's peeling off and reducing. Okay. We installed these out at Montezuma Wildlife, and of course this is a wetland that's very low oxygen, the buildup of organic matter, and hence there's no oxygen to act as an electron acceptor, and so iron gets reduced here. So that's pretty cool. So another, carrying on that idea some further, someone decided to do this with manganese. Okay? And so manganese is the same thing. You reduce manganese and it peels off. And here you can see where this material peels off, this black manganese coating. Okay? When it's reduced, it peels off. And again, visual representation of reduction by manganese. These were in the field for 4 days and taken out, and all this paint scraped off by reduction, peeled off. Okay. And here they are together. Here are the iris tubes and the myris tubes. Okay. And you can see this peeling off and reduction. So that's kind of another way to visually assess and this idea of reduction. Also, this goes on a little further. We can actually take photos of these and then look at the relative amount of area where the paint has been missing. Here's actually a buildup of pyrite, kind of interesting. Okay? But another way to assess aeration. So well-drained site, you don't see very much peeling off for manganese. Okay. Okay, so we've visual. Now we'll come back to the numbers. Wanted to give you a little break from numbers, and we'll come back to it. And we could ask the question, what is the EH of a well-drained soil? What is the EH, the redox potential of a well-drained soil? Okay. And so let's think about what's going on. So here I show the oxidized form of a variety of elements. Here's oxygen, nitrate, manganese +4, iron +3, which you've heard about, sulfate, and carbon dioxide. Okay. When you reduce oxygen to water, okay, this occurs around an EH of 0.38 to 0.32. Okay. So once you get below that, once you reduce all the oxygen, there's nothing left to reduce. You end up with water. Okay. So in this range, 0.38 to 32 volts, okay, that occurs. Or how many millivolts? How many millivolts is 0.38? Matt, how many millivolts is 0.38? Yes, very good. 380. Okay. How many millivolts is 0.32 volts? Yes, 320. Excellent. Okay, so you're familiar with that. Okay, so all the oxygen is depleted in the 0.38 to 0.32 volts, and now we're getting below that. All we have left is water. So the next thing down the line, ready to accept electrons, is nitrate, NO3-. And nitrate is reduced to N2. Okay, so nitrate is reduced to N2. It gets the electrons from somewhere, from respiration, anaerobic respiration, and we make N2. This happens when this occurs. It's in the range of 0.28 to 0.22 volts. Okay. So nitrogen is going along, being reduced, nitrate's getting reduced. Finally, you reduce all the nitrate. You get rid of all the nitrate in that system, and you have N2. Okay. And what's left? So it cascades down the line. So the next thing, the next material ready and waiting to accept electrons is manganese +4. Okay. Manganese +4 is getting the electrons that are now being very slowly made from anaerobic respiration, and it's being reduced to manganese +2. Okay. +4, +2. Note this is a gain electrons. It's being reduced. Okay. And in the range of 0.22 to 1.18 volts, this occurs. So the system chums along, and all of a sudden, all the manganese +4 is reduced, and all we have left is manganese +2. Okay? So what's left to get electrons? It jumps down to the next thing, and it's iron +3. Okay, so iron +3 is now accepting electrons in aisle 2. Iron +3 accepts electrons, and all the iron +3 is converted to iron +2. This is in the range of 0.11 to 0.08. Okay. Okay, so we exceed that range. We end up with all the iron being reduced to +2. What's left? Cascades down. Now we're down to sulfate. So sulfate now is accepting electrons. Sulfate is reduced to sulfide, S2, and hydrogen sulfate. And voila, now we're in the range of 0.14 to 0.17, but we're negative. We're getting even slower in the redox potential. When we get rid of all that, we're down to sulfide and hydrogen sulfide. Voila, CO2 is left, and CO2 is reduced to methane. Okay? Now we're really low. We're -0.2 to -0.28. Okay? So we've gone from this high potential, 0.38, all the way down to this low potential, to EH. And we see the numbers changing, and as we get successively more and more anaerobic, okay, your system has tendency to reduce more and more. You get to negative numbers. We go from O2 all the way down to CO2. So thinking about this, if we look at what's happening and we have a well-drained soil, so the question is, what is the EH of a well-drained soil? Okay, can you look at that graph, look at that slot, and kind of think, where are we well-drained and where do we start to go away, we get away from the well-drained condition? So the question on the floor, what is the EH of a well-drained soil? If you would go down this chart and kind of come up with a number, what would you propose? Put on your thought process. Okay? If you think about it, it's somewhere in the range of 0.4 to 0.7. And why do I say that? Why do I say a well-drained soil EOH is somewhere between 0.4 and 0.7? Okay? Well, look at what happens with oxygen. Oxygen is reduced to water when you get in the range of 0.38 to 0.32. So above 3.8, okay, there's plenty of oxygen around. But oxygen is starting to be reduced, right? So as you dip below 0.4, oxygen is being reduced to water. Okay? And that's where we start to see the depletion of oxygen. And it gets all depleted, then we're down to nitrate accepting electrons. So here's the answer to that. The EH of a well-drained soil is somewhere greater than 0.4 volts. Or how many millivolts? 400 millivolts. Okay? And so as we get smaller and smaller numbers, more towards negative numbers, we're getting more and more reduced system. So this is another way to assess the system of the capacity of a system to oxidize or reduce. Well-drained system, well aerated, greater than 0.4 volts for EH. Pretty awesome. Now we've added another number to our toolkit that'll allow us to take a measurement and decide whether we have a well aerated system or not. How cool is that? Okay. So now we've quantified it. Let's think about the factors that are impacting aeration. Okay, we've got a way to think about this a little more deeply now that we can quantify it. So let's go on with this train of thought. Okay. And so the first thing we think about, we have to come back to macropore space. Okay. And so macropore space, we're back to soil physical properties, right? We're back to texture and aggregate stability, bulk density, and organic matter. All those things we said that contributed to macroporosity, large pore space, pores that hold water against gravity. Okay. And depth in the profile. So we're connecting with physical properties, and now we're adding this idea of aeration. Okay. So that's the physical matrix. Now what's happening within that matrix? Now we have a lot of biological activity go on. So the rates of biochemical reactions are going to affect that. And so what's happening microbially? We have roots respiring. We have other organisms respiring, producing CO2, consuming oxygen. We have materials decomposing. All that organic matter going from the OI to the OA is being decomposed and synthesized. That's all generating it. So the level of biological activity, biochemical reaction rates, that impacts this soil aeration. So the two things together kind of give us a way to think about or assess soil aeration aside from numbers. Okay? So we think about texture. What about sands? We think about sands as generally having a large macropore space, okay? And generally should be well aerated. And then we think about silts and clays and fine textured soils, and we think about aggregate stability. So good aggregate stability, a lot of nice well-developed granular structure. This contributes to aeration. So again, texture is modified by structure, and we've been saying this all along. And now we're kind of carrying that through to the idea of aeration. So we're connecting macropore space, micropore space, and aeration, and we're adding one more layer of understanding to productivity of a system. So remember that systems that are able to transmit, or well aerated systems, are very productive because they're not limited by lack of CO2 or lack of oxygen or the buildup of CO2. Okay, so now we're making this link. So put this link into our system, our series of factors that affect productivity. Okay, we'll move on into season. Okay, so there are obvious seasonal rates. Things are high in terms of high temperature in the summer when we have plenty of energy around, a high rate of biological activity, and as that drops off both on spring in the early part and later in the fall, those levels of consumption of oxygen and CO2 drop off. So I've got a nice graphic that kind of explores this in terms of corn. Okay? So this is from figure 710. And this describes what's going on with some measurements in a cornfield in Missouri. Okay? So here we are at depth. So we said depth is in effect. And here we are with season. We'll go from June to November. Okay? June 1st to November 15th. And this graph shows the relative concentrations of carbon dioxide. So remember, carbon dioxide is produced by metabolic activity. Respiration of sugars produces carbon dioxide, and that is a sign that there's a lot of activity going on. Okay, so we start out here in June, not too far after planting and the crop is starting to develop, the canopy starting to develop. And we see the concentrations of CO2 at the surface, 0.3 to 0.5%. Okay? And we see the typical increase, so CO2 concentration increases with depth. Okay, does that make sense? CO2 concentration increases with depth. Okay? And why does it make sense, or does it make sense? So what happens with macropores and total pore space? Okay? So macroporosity generally decreases with depth, right? Structure decreases with depth. What happens to bulk density? Bulk density and depth. Bulk density increases with depth. Okay, so this makes sense. So carbon dioxide builds up. There's less macropore space. Okay, there is less total pore space with depth, and so we expect that the CO2 would build up. There's less capacity for exchange. Okay, we get into June 20th. The canopy is fully expanded. Okay, and the levels of carbon dioxide have shot up markedly. We've gone from 0.3 to 0.5% to 2 to 3% in the surface, and it's more than 7% down here in the middle of the root zone. Okay, then it drops off. So here's the impact of biological activity. Intense biological activity in root development, okay, here exceeding the capacity of the system to vent, to remove CO2. Okay, so maximum biological activity as we're getting to reduce macropore space, increased density, and so we get this real high concentration of CO2 in this cornfield, greater than 7%. So if that gets up, what's the cutoff? If it gets to a certain height, it's going to kill the root growth or stop the root growth. What's that number? You can look back in your notes. We just talked about that not too long ago. 10%. Okay, so greater than 7, and we're hoping if we get above 10, we're going to have trouble. Okay, so we get here, the fruiting is happening, the canopy is starting to slow down a bit, the fruits, all the activity is going to development of fruit, and the carbon dioxide, the root activity is slowing down, so the carbon dioxide is dissipating a bit. Now we're back down to 1 to 2% in the surface, 3 to 5% in that maximum zone of activity, and down deeper at 1 to 2%. So we come into September, time for harvest, and we see this continual drop in CO2. Then finally in November, we see the expected pattern. All the biological activity is pretty much slowed down. We're going into a cold part of the season. Everything's been harvested, and we see this reduction. So this plays out. We see 3 factors that affect. We see the effect of depth. We see the effect of season. And within season, we see the combined effect of high concentrations and the ability to, or the limited ability to vent CO2 and to get oxygen in there. So these 3 things play out in this graph, and it's a very illustrative graph that kind of combines the impacts of depth, biological activity, and seasonality. Here's a question. 7% CO2. How much higher is that than atmospheric? How much more higher? A couple hundred times, right? 350 parts per million. Okay. Big change, big change. Let's look at the forested system. Okay, so that's a pretty intense system. Corn, you see those as canopies and just very densely spaced plants. Let's compare that to a forest system. And so these data come from Bear Brook Watershed from Maine. So one of our research sites in Maine, we're looking at nutrient cycling and impacts of acid deposition and a whole bunch of other things. But one of the things we were measuring was the soil CO2 concentration for a variety of reasons. Okay, and this shows a seasonality. We go from January to December, okay, so pretty much a year. And the soil air CO2 concentration, okay, so the atmospheric CO2, microliters per liters, okay. You would know that as part per million, right? Microliters per liter. Okay. And so here we are by horizon. So we have the O horizon, okay, and that has the lowest levels. And then the B horizon, okay, going down to the solum, a little bit increase, and then the C horizon. Okay, and this is the C horizon. It's starting to get fairly dense, and it's not too far. And below that is a CD, a dense basal till and bedrock. Okay, so we see the typical pattern. Okay, so we see a seasonal pattern of increasing CO2 production that kind of peaks in the midsummer. Okay, and the deeper the soil, the later the peak, okay, because the rate of exchange is much slower. So higher levels of CO2 deeper in the soil. Okay, the concentrations peak later in the season, okay, and it takes longer to get that material out. Okay, and then we go back toward the non-growing season. But look at the difference in concentration. Here are 2,000, 3,000 parts per million. Okay, that's a long way from 7%. Okay, so convert this to percent. You might be surprised. So if we have 3,000 over a million, okay, what's the percentage there? 0.03. Okay, so that's a big difference. So these concentrations in forest system are much, much lower than in an ag system. And the same kind of patterns, they increase with depth, okay, and they show a seasonality, but the rates of CO2 production in this system and the rates of transferring that material out are much higher than in that corn system. So the corn system is going to have less macropores, okay, it's going to have less total pore space, and a very high level of metabolic activity, and the ability to vent that material, that CO2, is much reduced in that corn system. And this is a real nice illustration of that. Okay. So I'm going to assume that you're able to convert parts per million, 3,000 over 1 million, to percent, which would be parts per 100. Okay. How much more than atmospheric? Okay. That's the next question. So what's the atmosphere? 0.035%. Okay. So what is that, 10, 20? Okay, that's a question. Okay, we've quantified it. We've looked at different systems. We've looked at some interesting ag systems. We've compared that and contrasted that with forest systems, that red spruce stand in northern Maine at Bear Brook Watershed. Big difference in terms of concentration, but the same kind of pattern, increasing with depth, but a much more intense system with that lower rates of lower macroporosity and the higher rates of production in that very intense corn system. And so now we'll think about the impacts of poor aeration. Okay, so we've quantified it, we've defined it, and now we'll talk about the impacts. Okay. So the first thing is root growth. And we kind of alluded to that with the oxygen diffusion rate. So the first negative impact is reduced root growth. Okay. So CO2 builds up. Then, of course, roots are the structures that are scavenging water and nutrients. And so if they reduce their growth, their ability to scavenge water and nutrients, that reduces the productivity of the system. Okay. Okay. So not only is the growth reduced, but the capacity to take up nutrients is reduced. Okay. So that's, and of course, if you are depending on root materials to run stuff for upper operations, photosynthesis, all this material requires the stuff that you're absorbing from the soil, it's going to slow down or reduce total productivity. The other thing that's happening is that rates of cycling are reduced. So not only are the roots aerobic, but most of the organisms that decompose and synthesize humus are aerobic. And when you reduce the capacity of those to operate, organic matter builds up. So consider the wetland. We talked about wetlands, and that's the organic matter production is greater than decomposition. Organic matter builds up. So when that organic matter builds up, that's not bad per se, but what's happening is in all that organic matter is storing essential elements, nitrogen, phosphorus, potassium, and it's locking it up. So the rates of nutrient cycling are much slower. And so the productivity of the system is much slower. And we talked about this idea kind of between the forest floor humus horizons. We talked about the mull forest floor types with a very rapid rate of nutrient cycling. Forest later hits the floor and then is just decomposed very rapidly. All those nutrients are cycled through the system. We contrasted that to the moor forest floor, very acidic, buildup of organic matter, very low decomposition rate, and all that material being locked up in the organic matter. Okay, so very rates of cycling very slow, so the rates of productivity are very slow. Okay. And then the other thing that happens in a poorly aerated situation, toxic materials. Things like carbon dioxide, which we know is toxic, but there are other things, methane and hydrogen sulfide, there are other trace gases that build up and are toxic. So the impacts of poor aeration go beyond simply carbon dioxide. There's a lot of other gases. There are many other gases that are detrimental, and some of those are greenhouse gases. And we know methane's one you're very familiar with. Okay? And so those things build up. So poor aeration has some negative impacts, particularly if you're trying to maximize biological productivity and maybe you're trying to grow food, maybe you're trying to grow trees. Here's another negative impact of poor aeration, and this is a thing that is much more common than you'd believe, but this is the typical construction of new housing and subdivision. So not only is land being taken away from agriculture and production of food and fiber, here we have the death of a tree. It's coming shortly. So contractors, being usually woefully ignorant of root systems and the need for aeration around root systems, tend to pile things. Here's a dumpster filled with all kinds of stuff, and to get to that dumpster, things, people and organisms and all these cars and vehicles drive all this. So what's happening here? The soil is being compacted, the macro porosity is being driven down to practically nil, and the aeration is being tremendously reduced. So that aeration, 2 years later, the contractor's gone. You've paid $100,000, $200,000, $300,000 for your new house, and now you have to pay a couple $1,000s to remove this tree that looks so nice when you constructed your house, but now looks so unnice when you're looking at a lawsuit and dead limbs and people walking around. So that's a pretty negative impact, and it's the cost usually borne by the homeowner. A little bit of foresight and kind of care for construction. It wouldn't have taken much for that contractor or someone looking over that contractor to isolate this area with tape or flagging and say this is a no traffic zone. So right now it's a no use zone. Okay. So let's think about some management alternatives. Okay. So good planning would have prevented that, and that would have saved a whole lot of trouble and probably a couple of lawsuits. Okay. But there are ways to improve aeration, and one of those is to improve drainage. So how do we improve drainage? So typically we do this by ditches or by tiles, drainage tiles, or by raised beds. So there are a number of solutions, management solutions that can be provided that can counteract or alter the negative effects of poor aeration. So here it becomes a question of economics. Is the price of improving drainage worth economically? Is the result of that either increased growth or increased land use class? Is that worth the effort? In forestry, we deal with the conditions we have rather than alter the conditions. So mostly in forestry and some part of horticulture, the appropriate way to deal with poor aeration is to manage for the appropriate species. That is, you can favor species that are able to compete successfully in poorly drained conditions. Okay? It's a low-cost solution, but a rather effective one. And when you're dealing with thousands of acres to manage, there's not very much opportunity to invest money in terms of installation of drainage ditches. But there are opportunities, have been done in the southeast. So here's an illustration of improved aeration, and one of these ways is to actually have aerators or tubes that are perforated, and this provides a way to deliver air, and it's a rather simple low-cost solution to improving the aerobic capacity for this below ground. See, this is a clay soil. We know that clays tend to be fairly low porosity, low permeability, and tend to hold water and be poorly aerated unless you deal with them. So one way to aerate them is to add some better quality soil and also provide a connection to the atmosphere in these so-called breather tubes. So that's a simple low-cost solution to improving aeration and probably have a positive impact on this tree. So in lawns, this is done by actually taking out little divots. And note, this doesn't compress the soil, but these actually are little kind of little core samplers that remove cores and will increase the aeration with very little negative effect. You don't have these large holes, very small holes. This is commonly used in lawns and turf. But it's not all bad. There are some positive aspects of poor aeration, and we see those as wetlands. Okay? And so wetlands are soils, the definition of a wetland, soils that are water saturated near the surface for prolonged periods when the soil temperature is greater than 5 degrees C. So that's a wetland. Okay? So it leaves a lot to be desired in terms of telling us exactly what a wetland is. So water saturated, that's pretty easy to tell. And near the surface. So the question is, how near the surface? And prolonged periods. And the question is, how long? And because in order for this to develop, these wetland conditions, the soil temperature must be above 5 degrees C. That's when biological activity starts cranking. Okay? So that's the definition, but it needs more. It needs more to tell us what is and is not a wetland. So in order to further expand on that, said we need a little more guidance. Do we have a wetland? And so there are 3 characteristics that are used by the Corps of Engineers to decide what a wetland is. And you have to meet 2 of the 3 of these. So we need wetland hydrology. That is, the water has to be present to create those saturated conditions. Okay? We need hydric soils, which are poorly and somewhat poorly drained soils, and hydrophytic vegetation. So this is the key. This is the test for identifying a wetland. Meet 2 or 3 of these. Okay? And then your jurisdictional, you have a wetland. Hydrology, hydric soils, hydrophytic vegetation. Okay? And so I say, oh, okay, they're helping me a little more, Briggs, but that's not enough. And I say, I agree. So I better tell you about hydric soils. Hydric soils, check out this definition. Okay? You thought the definition of wetland was pretty loose. How about this? Formed under conditions of saturation, flooding, or ponding. Saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. That's about as useful as the definition of wetland, right? Flooding, ponding, are long enough. So how long is long enough? Okay, to get anaerobic conditions. And what's the upper part? Is it the upper 10 centimeters, the upper 20 centimeters, the upper 30 centimeters? So we need more. So this is just not enough. And so we need indicators. So something to help us decide whether this occurs, saturation, flooding, or ponding, long enough to develop anaerobic conditions in the upper part. Okay. So let's get a little further. So saturated and reduced. Soils that are saturated and reduced are hydric soils. Okay. Still not enough. Saturated and reduced. Okay. So we need indicators. So we've developed, the soil science profession has developed a series of indicators to say that these conditions occur. So what are these indicators based on? Well, morphology. You can see things in the field, and so morphology becomes critical. When we were looking at horizons, and we learned how to differentiate the BH and BS from a VW, morphology was key, right? We needed an E horizon, and once that E horizon was there, we needed a certain color, a certain redness, to decide that we had a BS horizon. Okay? So those are criteria that helped us along to differentiate. So it's kind of the same way with wetland soils, okay? And these hydric soils, we need some criteria that suggest that these conditions exist. Okay? And so that developed into a whole subfield of hydric soil indicators that we're still looking at. And so I'll kind of relay those or describe those to you now. Okay? So these are morphology-based observations that allow us to think about loss accumulation of iron, sulfur, manganese, and carbon. Okay? So these are the key things. So how do we know morphologically whether we're losing or accumulating iron, sulfur, manganese, or carbon? So there are a couple of key things. Okay? And one thing is in terms of organic matter and color. Okay? So here's a pretty interesting graph that relates hydric soils to several indicators. Okay? It relates it to the moisture regime, okay, per aquic, always saturated, and aquic, saturated in the upper part. Okay? To organic matter, okay, and glaucoma. So a hydric soil in peraquic and aquic moisture regimes, saturated most of the year, okay, or fully saturated, or have a Gley chroma, so chroma less than 1. And we talked about Gley. We talked about iron reduced, iron +2, having a very gray color. So if there is this Gley chroma, the matrix consists of this very low chroma iron. That's a morphological indication of iron reduction. Okay? If you have chroma less than 2, okay, in concentrations, you get some of that in aqueous mortars. So what's a concentration? A concentration is small spherical collections of iron. Okay? So nodules and concretions, the same kind of thing. A nodule is this very round hard, it's like a BB, and a concretion is like a BB that's layered. Okay? So if you see a lot of these nodules and concretions, you get them in hydric soils, poorly drained conditions. So these are indicators. These are some of the indicators. A lot of organic matter is an indicator. Why? Organic matter builds up and doesn't decompose in the absence of oxygen. So the high presence of high concentration of organic matter gives us an organic soil. Gives us a hydric soil. It's an indicator. Okay. So remember, low chroma. So we talked about this. This is the Munsell color chart. And we had various U's, 10, 7, 5YR, 5Y. And low chroma are those in the two left hand, chroma 1 and chroma 2. These are the very gray colors. Okay? And for any value, for any degree of lightness, whether you're on 10R, there's the low chroma for 7, 5YR, low chroma for 5Y. Okay, it's these left two columns. Those are low chroma. This morphological indicator of reduction because of the reduction of iron. So let's see how that plays out in the field. Okay, here's low chroma. See these grays? This is low chroma. Okay, we also have these oxidation lines. Okay, but the matrix is more than 50%. This Gley, low chroma. This is hydric soil. Okay, here it is again, and here's oxidized root spheres within that. And of course, this is the plants are able to bring oxygen, some of these plants, down through their parenchyma. That oxygen goes to the outside of the root, and it's oxidized, and everything else is reduced. So a little bit of oxygen there, and that's another hydric soil indicator. Pretty cool. Okay. Here we look at the relationship with EH. Okay. So here is water, okay, standing water. There's a little bit of an aerobic zone right near the surface. Transition then largely anaerobic. Get a root channel, so oxygen is pulled into the root, oxidized on the edge, and this has a very low EH, negative EH. So if we go back to that last picture, that's what we're seeing here. A very low EH, reduced iron, oxidized at the root, and we see a picture of that here. So there's a whole book, a whole series of illustrations of field indicators of hydric soils in the United States. The last version was 2006, and it goes through all these, and these are constantly updated and worked on by a soil science community. And practically every season in every state you can find a workshop that applies some of these indicators. At least in Maine, the Maine Association of Practicing Soil Scientists regularly at its workshop and field meeting will look at these field indicators at various sites and help everyone to calibrate. And it's an active area of research, a very applied research that is continually updated. And again, most of the state soil science societies will have some kind of field tour that you can get involved with, and it's pretty neat. And it's the old redneck, you might be a hydric soil if you have a depleted matrix, okay, so depleted of iron, okay? Or if it's sandy and gleyed, okay? Okay, so we've pretty much talked about hydric soils. We've gone through our definitions, given you some examples. Okay, and now we need to spend a little bit of time kind of fleshing out soil moisture regimes. And we've already had kind of an intro to this in the last soil moisture lab. We looked at several soil moisture regimes and calculated the deficit, a precipitation deficit, the amount of water you need to add to irrigate. And so now we'll explore some of those regimes in a little more depth, okay, to kind of fill you in with that. And so we have the aqueous moisture regime. Okay, so this is a reducing regime. That is, iron is reduced, lacking oxygen, and so pretty much no dissolved oxygen. And why? The saturation. So if all the pores are filled with water, there's no air. And remember, diffusion occurs 10,000 times greater in an air-filled pore space compared to a water-filled pore space. Okay? So once you use up the dissolved oxygen, that's it. What happens? Nitrate's going to start accepting electrons. Use that up. What happens? Manganese is going to start accepting electrons, so on and so forth, all the way down to CO2 and methane. Okay? So that's aqueous moisture regime, virtually free of dissolved oxygen due to saturation. And this can be seasonal. You get fluctuations in the water table. In the spring and the early summer, the water table is high. It sinks low. Okay, so we can still have an aqueous moisture regime due to these seasonal fluctuations. Virtually free of dissolved oxygen. Paraqueous. Okay, paraqueous is continually recharged, and usually we're looking at groundwater at the surface, and we think about tidal marshes. Okay? So some other moisture regimes we've talked about: eutectic, eustic, aeritic, and xeric. And these we've talked about as being aeritic, very dry; xeric, seasonal distribution, Mediterranean type climate; eutectic is fairly moist, and eustic kind of burnt. So these are the other ones, and again, we looked at these four in our soil moisture lab last week, or 2 weeks ago now. I'm 1 week ahead of myself, or maybe a week behind myself. Okay. So now we think of wetlands. Okay, so we've had all the negative impacts of poor aeration. Now we've got to think about some positive impacts, right? It's not all bad. The glass is half empty or half full, right? The beer can is half empty or half full. And so we think about the positive impacts. And so wetlands are one of the very positive impacts of poor aeration. Okay? So we think about what are wetlands, okay? These areas that are continually flooded, saturated, ponded, and their dissolved oxygen is depleted, organic matter builds up, but these have important functions on the landscape. And one of these is for habitat of species. There are a variety of species that compete very effectively in these conditions. And those types of plants, hydrophytic plants, and vegetation, prospers and competes and does very well in wetlands. Okay, the second thing they serve from our point of view, ecosystem services, and that's water filtration. Okay? So these systems are responsible for cleansing water. We actually take advantage of this. We've constructed artificial wetlands to treat wastes, okay, to process water and clean it out. So this is an extremely important function in terms of water quality. Okay? There's flooding reduction. So wetlands provide a buffer against flooding. As wetlands, as water levels go down, okay, the capacity for storage and flooding goes up. So this flooding reduction, this provides a buffer against large inputs of water in the drier parts of the season. Okay? There's also shoreline protection. Some of these marshy systems, these marine systems, the wetlands provide shoreline protection by providing the vegetation and provide both a physical and chemical protection. Okay? And recreation. You think about all the recreation that occurs in wetlands. There are fisheries, recreation in terms of boating, the Everglades. There's a high recreation opportunity. And then finally, there are a variety of products from wetlands. We got timber, a lot of fish, and even some food. Actually, pineapples, but that's a whole other story and a problem. Okay? So these are the positive impacts of poor aeration. Wetlands, and wetlands serve in terms of improving and maintaining water quality, and also have some aesthetics and recreational aspects. Okay? So it's not all bad. Got to look at the positive impacts. All right, that takes care of soil aeration. Okay? We've gone all the way through talking about a well-defined, well-aerated soil. We've defined it. We've talked about the factors that influence it. We've given you a way to quantify it. Okay? We've then talked about some of the positive and negative aspects. We talked about potentials for management, these economic possibilities, and finally close with the positive aspect of wetlands. Now, next week in lab, we'll be visiting our only trip to an organic soil. and we'll talk a lot about wetlands. We'll see some of these organic soils and what the result is, and we'll talk about their management and also mismanagement. And that'll be pretty much our last field trip. And this lecture here, this discussion, kind of sets the stage for that. There are some things on the web that we have, hyperlink to that you'll want to look at before we go on that field trip. Again, this is one that's 100% grade participation, and so as long as participation is good, the grade will be there. And it gives you a little bit of break in terms of field lab write-ups. And also gives you a little bit of time to think and focus on studying for the next exam. Okay, remember the next exam is November 5th. We've covered now soil physical properties, right? We've covered temperature. Well, we will cover temperature. We've covered aeration. So there's a big chunk of material on this next exam that'll go through the material in these next few lectures. So again, the importance of studying early and kind of reviewing is paramount to your success. You can't cram for this. So that's my little commercial. It's time to think about and reviewing this material. And again, I will have the review session Friday. I'll be back Friday, and I hope to see you there. And so let me continue on then with soil temperature. Soil temperature, it's a hot topic. Oh yeah. Okay. So why worry about temperature? So it's all about energy, right? And so when we think about temperature, we're thinking about the physical, chemical, and biological processes. Many of these things are energy-driven, temperature-driven. There are some negative things. Winter burn is all about soil temperature and air temperature differences. When we get these warm soil temperatures, but the air temperature is still freezing, we can have, and vice versa, we get some strange things going on. We actually have winter burn. So the air temperature warms up. I said that backwards. The air temperature warms up. There is no transpiration going on because the roots are still inactive. Foliage heats up and you get winter burn. So one of the important concepts to think about temperature we've discussed earlier in terms of weathering, but we'll revisit now, is Q10. Right? This idea that the rate of chemical reactions tends to double with each 10 degrees C temperature increase. So that tells us that temperature, energy inputs are important for a whole lot of reasons. So our biochemical reactions double with every 10 C degree increase. Here's the thing I'm going to close with. Okay? I'm going to close with soil temperature and the critical temperature. So we think about, we've made all this distinction in terms of wetlands and 5 degrees C and biological zero. So we've made this distinction that biological activity starts or tends to begin in earnest at a certain temperature. And this temperature for most processes is 5 degrees C, 40 degrees Fahrenheit. Okay? It doesn't cease, biological activity doesn't cease below 5. Okay? There's stuff going on at 0. There's stuff going on for some organisms at minus 5, minus 10. But for the most part, the bulk of biological activity is really reduced and doesn't really get started until you hit that 5 degrees C or 40 degrees Fahrenheit. So this is an important number to have. Okay? Things like nitrification, the conversion of ammonium, NH4 plus to NO3 minus. Nitrification. We'll look at this in detail next month. This doesn't really get started in any kind of rate until we hit this 5 degrees C. Things like root nutrient absorption and uptake doesn't really get going until you hit 5 degrees C. Again, it's a general, it doesn't stop at 0, doesn't go to 0 below 5, but it really slows down. So this is an important threshold. Okay? Root growth and development. So with that, we're going to close, and we'll pick up soil temperature next week. And this week you should be reviewing, getting ready for the soil review session on Friday. I'll see you then. Hopefully all is well. And I wish you a wonderful day. And we're over 1/2 way through soils. And as we conclude here, we're going to start to head into chemistry. So this is a really good time to begin reviewing what we've had so far, get that all compartmentalized and kind of registered in your minds, because the next phase of this is soil chemistry, and you'll want to have all this physical material kind of in place as we go on the last piece towards understanding production, productivity, and biological activity. So have a great day, and for all of you that fell asleep, wake up! See ya.